Hello again, this is the next session of the course on nanoelectronic device fabrication and characterization, and we have been discussing nanostructures and the formation of nanostructures. And last time we went on to discuss the formation of nanowires by the vapor liquid solid method and followed by the solution liquid solid method. We also pointed out that there are variations of these methods that use, for example, lasers to assist the formation of nanowires, and then we went on to discuss the formation of nanowires and nanostructures in general by the solution process, where the assistance of microwave radiation is used to obtain nanostructures of high quality much more rapidly by the microwave assisted method than by other methods. What we shall do this time is to discuss some general aspects of nanomaterial preparation, and then go on to carbon nanostructures and thin films. We have already discussed aspects of heterogeneous nucleation, which is where they come in the context of thin film deposition, which are very important for nanotechnology in general, device fabrication in particular. And then we will try to deal with the physical vapor deposition, chemical vapor deposition and atomic layer deposition. Now, some general comments. We have discussed bottom up methods, and mostly so far we have confined ourselves to the discussion of different chemical methods that are bottom up in their approach. It is useful to note that there are physical methods that are capable of producing nanoparticles and nanostructures. As listed here, vapor and gas condensation, that is, you have vapor which generally involves high kinetic energies and therefore correspondingly high temperatures, and you suddenly subject them to cooling, condensation. And if you do not allow that condensation to take place over a relatively long period of time, that is, if you quench it, then in the absence of time for these atoms in this condensate to relax into crystallographic positions, proper positions, you often get either nanocrystals, very small crystals, or you get amorphous material. Jet pyrolysis is really much the same. You have a jet of particles moving at a high speed, which means high kinetic energy and high temperature, and then you suddenly cool it to obtain a condensate that would contain nanocrystals or even amorphous materials, as I just mentioned. The quenching of metal alloys to obtain glassy metallic materials known as met glass, which is actually an important part of technology for important part of materials technology. That is a physical method where one obtains nanostructured material through quenching. Thermal evaporation. We have discussed evaporation and condensation. Again, thermal evaporation of let us say metals or metal oxides or some such material in a vacuum system, which is often the way to produce thin films of these materials. Suppose you collect these evaporants, including metals, on a cold substrates. Normally, this is done on substrates that is at room temperature. In a high vacuum, one evaporates material and collects it on a substrate often held at room temperature. But suppose you deliberately cool the substrate, then again these particles that are full of kinetic energy and therefore correspondingly high temperature, they get quenched and usually get thin films now with nanostructured material. Laser evaporation is also the same thing. Lasers pump in a huge amount of energy into the target at which they are aimed, and therefore, there is instantaneous evaporation of the top layer of the material when it is bombarded by the laser. And if one collects this material and one collects it on a substrate that is not heated, then once again one can get nanostructured material, or even when it is heated, even when the substrate on which this laser evaporated material is collected is heated, even so it is possible to obtain nanostructured material. Indeed, an important part of thin film technology, a physical method of deposition of thin films known as pulsed laser deposition PLD, is based on this laser evaporation technique. Now, most of these techniques that are listed here, except really that of the technology of met glass, they are of low yield. So, you do not get much nanostructured material given the amount of material one starts with. They may require elevated temperature subsequently to obtain useful nanostructured material, and often involve costly apparatus for synthesis. But all of these constitute physical methods that are bottom up in nature. One of the things to remember, which I am not sure that I alluded to earlier, is that nanostructured material, nanocrystalline material, that is, whether it is formed by a physical method or a chemical method, as long as it is a bottom up method as opposed to a top down method, where for example, one uses ball milling to cut down material to very small sizes. In such cases, as we mentioned at that time, defects are induced. But if you consider nanocrystals of dimensions of the order of a few nanometers produced by, let us say, the solution based methods, as in the case of metals or in the case of compound semiconductors, the Sol-Gel method and so on, which we refer to, or even the microwave assisted solution based processing. In all these methods, the crystals that are produced are of very high quality, which means technically that they have a low density of defects, and that is in a way natural if you think about how atoms are progressively assembled into a periodic array. If the array is large, very large, let us say you are talking about a crystal of the order of a, let us say a centimeter in size, containing Avogadro number of atoms. Then as the assembly process proceeds, as the atoms come together to form such a macroscopic crystal, the chances of defect formation, such as dislocations, that is atoms in the wrong place, wrong crystallographic phase. So, the chances of defect formation are increased when the total number of atoms that are assembled together is increased. So, in a crystal that has around the Avogadro number of atoms, then naturally the chances of formation of defects is much greater than in the case of a nanocrystal, which might have, let us say, 10,000 or 50,000 atoms. So, in general, given the scale of these crystals, they have few defects, much fewer. Therefore, nanocrystals are generally more perfect than macroscopic crystals of the same material, and that is important to keep in mind because it has consequences. We will come back to that. We come to carbon nanostructures. Carbon is a truly unique material, as you know, in terms of its chemical reactivity and ability to form compounds with virtually every element on the periodic table. Even so, it has been even though it has been known for a very long time, carbon has really thrown us surprises in the recent decades with the discovery of buckyballs, carbon 60, carbon 70, carbon 80 and so on, carbon nanotubes soon thereafter, and more recently the discovery of graphene, a truly two-dimensional carbon structure. All of these are showing up to be very important technologically, and certainly of course, there has been a very considerable amount of new science that has come out of these carbon structures, carbon nanostructures. Fullerenes first, C60, C70 and polymer forms, I mean polymorphs I should say, polymorphs of C80, one in a so called rugby ball configuration, the other one in an icosahedron configuration. These are all molecules of carbon with the respective number of atoms. So, these are macromolecules of carbon, and these have been investigated. For example, C60 has had the surprising property that if there is a metal that sits at the center of this or within this C60 shell, then it becomes a superconductor and so forth. Carbon nanotubes really have been much more relevant technologically speaking, and these were discovered rather soon after carbon the buckyballs in 1991, and these have unique material properties, and they are, if it is a single walled carbon nanotube, because one can also have multi walled tubes as shown in this cartoon. The one here is a multi walled tube, you have concentric tubes, whereas you have in the center an array of single walled nanotubes. If it is a single walled carbon nanotube as in the center over here, then it is as nearly a one dimensional structure as one can practically have, with diameters that can be as small as about a nanometer. Some features of these carbon nanotubes is that mechanically it is stronger than steel, multiple tubes can slide inside of each other with the minimal effects of friction. So, it can be a very good lubricant material. It can support electric currents of density 1000 times greater than silver or copper, and surprisingly it can have properties ranging from that of a metal to those of a semiconductor based on the configuration of the carbon nanotubes. So, these are some of the unique features of carbon nanotubes, which are, as I said, especially if they are single walled, then you have a nearly one dimensional structure. Now, what is shown on the left here is the hexagonal graphene template. This is the so called sp2 bonded carbon that sits at each of these vertices of hexagons over here. And what is shown on the right are three different configurations of carbon nanotubes that can be generated by folding this graphene sheet. This is actually the so called graphene sheet, that is, graphene is a single layer, a single two dimensional layer of carbon. In fact, graphene is obtained by literally peeling off layers of graphite with an adhesive tape, for example. There is a physical method of producing a graphene sheet. So, what is this? This is a graphene sheet, and by folding the graphene sheet along different directions with respect to the position of the atoms in this hexagonal lattice, As shown here, one can get, if the axis of folding runs through the atoms, then one gets this armchair structure of carbon nanotube, which is closed at this end. For example, one generally wants to think of carbon nanotubes which are closed at both ends. So, this end where it is closed is really half a buckyball. So, depending on the axis around which the graphene sheet is folded, you would get an armchair configuration or a so called zigzag configuration or a chiral configuration which lacks mirror symmetry. So, you have different configurations of carbon that can be derived quite readily by folding it along different directions of this two dimensional lattice, and one can describe these things in terms of the basis vectors A1 and A2 as shown here, basis vectors which will allow you to translate from any spot in the lattice, hexagonal lattice, to any other in terms of integral numbers of A1 and A2. The remarkable thing is that carbon nanotubes of the metallic type, or rather of the armchair configuration, are metallic in character, whereas the other two configurations are semiconducting in character. So, it turns out that if one produces single walled carbon nanotubes, if one manages to produce them, then about 1/3 of them would be of the armchair configuration and therefore metallic, and the rest would be semiconducting on the average. So, this is the remarkable property of carbon nanotubes, that they can be of both the metallic and the semiconducting types depending on the way they are folded. So, this is a further demonstration of the construction of nanotubes in terms of the primitive lattice vectors that I just described, A1 and A2. So, as shown here, you can have the zigzag configuration by folding it along the line that bisects opposite faces of this hexagon, and then the armchair I have described, and anything in between gives you the chiral symmetry. Okay. Therefore, this is the way one constructs the carbon nanotubes, and this is a further expansion of the same thing to tell us about the left handed and right handed versions, because there is no mirror symmetry, and that is the characteristic of folding the carbon nanotubes along a line that is between the armchair configuration and the zigzag configuration. A great deal of work has been done on these things, and these are now really textbook material. I mentioned that you can have semiconducting carbon nanotubes in the zigzag and the chiral configurations. What is shown here is the energy band gap. Semiconductors have energy band gap. So, this is the energy band gap as a function of the inverse diameter. So, we are talking about the diameter is increasing this way, because this is the inverse diameter. So, as the diameter is increased from low values to higher values, the energy gap falls from about 1.2 and approaches 0 as the diameter of the carbon nanotube is increased. What it really means in terms of this folding is that if you have a, for this vector, for example, N1 and N2, if N1 and N2 are large, relatively large, then you would have a relatively large diameter carbon nanotube, because you are folding it with many more unit cells in them. Therefore, that will have a larger diameter, and those ones with the larger diameter usually have a smaller energy band gap. One of the earliest methods by which carbon nanotubes were grown is the laser assisted growth method. What is done here is to take a graphite piece in which either cobalt or nickel particles are embedded, small particles, preferably nanoparticles of cobalt and nickel are embedded in this graphite piece, and this graphite piece is then bombarded with lasers. Remembering that the graphite piece itself is at a high temperature in a furnace and bombarded by this laser beam, then the graphite is evaporated, and then this evaporated graphite material is carried by the argon that is flowing through it as the carrier gas. So, this vapor of graphite that is evaporated is carried by the argon gas and it is condensed on a water cooled copper collector. So, it is a rather simple method, direct method of a physical kind. When this process is conducted, then it turns out that the copper collector collects single walled carbon nanotubes, and it turns out that cobalt and nickel catalyze the formation of carbon nanotubes from this evaporated graphite material. So, this is an early method of producing carbon nanotubes, single walled carbon nanotubes. Subsequently, chemical vapor deposition, chemical methods such as CVD were developed to produce carbon nanotubes, typically using a gas like methane as the precursor gas, and it turns out that a catalyst such as cobalt, nickel or iron is required to catalyze the formation of carbon nanotubes from the decomposition of methane, and the carbon that is obtained from that is then catalyzed into carbon nanotubes by these tiny particles of metals that are present, for example, on a substrate. You can grow nano wires or rather nano tubes of carbon by spreading nickel or cobalt or iron particles on, let us say, a silicon substrate which is heated to a high temperature, and methane gas, for example, is then made to flow over that one. So, this is the general methodology. It turns out that what is seen here is the two dimensional graphite lattice, which is actually the graphene sheet. It turns out that graphene, single walled carbon nanotubes, multi walled carbon nanotubes, all of these can be produced by essentially the same chemical vapor deposition method using a variety of precursors. That is, it is possible to employ methane, acetylene, benzene, ethyl alcohol, carbon monoxide, ferrocene and so on, a whole variety of carbon containing vaporous compounds, and then by slightly altering the methodology for decomposition and catalysis of these things into carbon nanotubes, it is possible to get carbon nanotubes, multi wall, single walled and so forth by the general CVD method, which works at around 700 to 800 degrees Celsius. This is actually a piece of apparatus, a chemical vapor deposition reactor, thermal CVD, that is, only temperature is used to conduct the reaction, as opposed to anything like a plasma CVD, where a plasma is employed to accelerate the process typically. So, in this furnace one places a substrate and then uses a gas, for example, here ethylene, okay, C2H4, hydrogen and argon. So, there are certain protocols over here that allows you to deposit carbon nanotubes on a substrate like silicon, at a temperature of about 700 degrees Celsius. The formation of carbon nanotubes by thermal CVD is really quite analogous to the vapor liquid solid method that we discussed earlier, except that this is not really there is no liquid formation. What happens is that in the metal particles that we mentioned, cobalt, nickel or iron is really most effective. So, this metal particle acts as the substrate on which, the surface on which the impinging hydrocarbon decomposes to produce carbon, elemental carbon. That carbon dissolves in the metal without the metal itself becoming liquid, and the dissolved carbon then emerges as a carbon nanotube, and the carbon nanotube grows out of this metal deposit. So, in practice something like this is done. One takes ferric nitrate and decomposes ferric nitrate to give iron particles on a substrate like that of silicon that is kept inside the furnace. So, that is the first step. You obtain a substrate and then you deposit, or you obtain a substrate that is decorated with nanoparticles of iron that comes out of the decomposition of the nitrate, and then one goes through the process of chemical vapor deposition using an appropriate hydrocarbon, and as a result of it, typically at about 700 degrees one gets the growth of carbon nanotubes by a process analogous to, as I said, the VLS process. It turns out that in such a system one can conduct these reactions under an applied electric field, giving rise to carbon nanotubes that are essentially perpendicular to the substrate. So, you can have a well organized array of carbon nanotubes going on a silicon substrate by having an applied electric field during the deposition process. So, what is shown on the left here is an array of carbon nanotubes produced by the process that was just described, and what is shown here in the inset is the Raman spectrum of the carbon nanotubes that are obtained, and it turns out that this particular signature, this particular spectrum is the signature of single walled carbon nanotubes. The multi walled carbon nanotubes have a slightly different signature, and therefore, from the Raman spectrum it is possible to tell whether what you have got is single walled or multi walled carbon nanotubes through a CVD process. Now, it turns out that depending on the flow rate of ethylene in the CVD process we described and the catalyst particle size that is employed in the process, depending on that it is possible to obtain either single walled nanotubes or multi walled nanotubes. So, it is possible to control the nature of the carbon nanotubes that are obtained by tinkering with the process in a predictable manner, as a matter of fact. So, what is shown here is a forest of multi walled carbon nanotubes that are obtained in the same chamber that was shown earlier, in the same chamber, by greatly increasing the ethylene concentration, that is the precursor to carbon nanotubes. By increasing the ethylene concentration, it is possible to obtain a forest of multi walled carbon nanotubes. What is shown here is a diagram that tells us how, for example, using a catalyst, metal catalyst which could be nickel, cobalt or iron, into which carbon of various types dissolve. For example, carbon atoms in the gas, carbon molecules in the gas, amorphous carbon, buckyballs, all these things can go into the metal particle at an elevated temperature and then come out of this as carbon nanotubes under appropriate conditions. So, this is really sort of a devouring of carbon, different kinds of carbon to yield carbon nanotubes. What is noteworthy is that if one had buckyballs, for example, then by a relatively small expenditure of energy, 0.045 electron volts, it is possible to fold it into a carbon nanotube, fold the carbon into a carbon nanotube. Whereas, the energy required for doing the same thing with atoms in the gas is much greater, several electron volts. So, if you had free carbon atoms, then a great deal of expenditure of energy is required to produce carbon nanotubes from such disordered carbon. What is shown here is how the CVD process allows you to grow carbon nanotubes around, let us say, a glass fiber in this case. So, what is in the center is a glass fiber, and all around that, as shown in this magnified photograph, carbon nanotubes have grown essentially perpendicular to the glass fiber surface. So, locally perpendicular. So, these things are done now quite can be done quite routinely, quite predictably by the chemical vapor deposition process. What is shown here is how the process of CVD, whether it is thermal or whether it is plasma assisted, can alter the topology of the carbon nanotubes. So, what is shown here is that initially this process is conducted as a thermal CVD process, that is, only temperature is used to conduct the chemical reactions that result in the formation of carbon nanotubes. Subsequently, as plasma is turned on, now plasma CVD being a more rapid process would then pick it up and then allow you to grow this kind of a forest of nearly parallel carbon nanotubes at a pretty fast clip. So, there are ways in which therefore, one can alter the process to obtain carbon nanotube structures. By the way, these carbon nanotubes can be as long as several hundred micrometers in length with a diameter of the order of 10 to 20 nanometers. So, the aspect ratio of these things can be very high. In fact, there are reports of how millimeter long carbon nanotubes can be obtained by suitably altering the process. So far, we have shown how using hydrocarbons carbon nanotubes can be obtained. What is shown here is how a different kind of a starting material, in this case ferric acetyl acetonate. I would like to recall to you that last time we used zinc acetyl acetonate to produce zinc oxide nanorods from a solution under microwave bombardment. MOCVD stands for metal organic CVD. So, this is a metal organic compound with iron at the core of it and then methyl groups as terminations. Now, it turns out that this is a subliming crystalline solid and one can employ this as a CVD precursor because it sublimes and produces vapor, and when that is done in a rather simple CVD reactor, where you have a high temperature over here for the substrate, and then you vaporize the ion compound and carry it with argon vapor and so on. So, when this is done in an inert ambient, that is argon and ion compound, nothing else, no oxygen and so forth. So, when the ambient is inert, then it turns out that depending on the pressure at which this reaction is conducted, it turns out that it is possible to obtain carbon nanotubes as shown in the right hand micrograph simultaneously with iron oxide. So, what you get is carbon nanotubes that are interspersed with iron oxide in a composite material. Now, when the pressure is changed, it turns out that this is now carbon nanotube rich. So, there is a smaller proportion of the oxide than of the carbon nanotubes. In other words, by using a different starting material altogether, not a hydrocarbon, it turns out that it is possible to obtain carbon nanotubes along with, in this case, an oxide to form a composite, which can be a very interesting material. Now, here is the Raman spectrum, and that Raman spectrum has signature of multi-walled carbon nanotubes here, and it also has a signature of iron oxide Fe3O4. Fe3O4 are these particles that are seen here. So, you have the simultaneous formation of Fe3O4 and multi-walled carbon nanotubes by this kind of a process. We move on to a somewhat general discussion of thin film depositions, because thin film formation is an important part of device technology, including nano device technology. There are physical methods and there are chemical methods. We have just now gone through the chemical vapor deposition process. So, there are numerous methods like sputtering and plasma enhanced methods, ion beam deposition and so on. Now, there are PVD and CVD methods with advantages for CVD over PVD and PVD over CVD. Now, one general feature is that in physical vapor deposition, you have, for example, in sputtering a target from which material is knocked out by bombarding ions like argon ions, and those particles of target material that are shot out of the target collect on the substrate to form a film. So, this is the physical vapor deposition method, where the material that forms the target becomes the material that forms the film. In the chemical vapor deposition process, you have some vaporous material, including gases, that flow through the reactor, as we have shown in the case of the carbon nanotubes, and they react on the hot substrate surface and produce film of the material that is the result of the chemical reaction. So, the material that is deposited is different from the material of which the vapors are allowed into the chamber, whereas here the material of the film is the same as the material of the target. One of the important features of chemical vapor deposition is conformal deposition. That is, if you have contours on the substrate, which of course is a very important part of semiconductor fabrication, then chemical vapor deposition is capable of conformally covering that contour on the substrate, that is usually a patterned contour. That is, you can have conformal coverage of all these features that are produced by patterning. Whereas, in physical vapor deposition, because it is a line of sight process, you have direct deposition, proper deposition on these surfaces that are normal to the flow of the vapor, whereas on these walls that are parallel to the flow of the vapor, you can have little or no deposition. So, it is not conformal coverage in the case of physical vapor deposition, and as you well know from the earlier part of the course, you need conformal deposition in order to be able to cover features in devices which are constantly becoming smaller. These are examples of where, for example, here you have a high aspect ratio hole that you have to fill with a material, and chemical vapor deposition turns out to be capable of doing so, which normally physical vapor deposition processes are not capable of doing. So, CVD has advantages of uniform deposition over large areas, and as we just said, conformal coverage and usually high rates of deposition and so on, and therefore, it is often the process of choice for VLSI fabrication, especially where high aspect ratios are involved. There are various kinds of CVD processes, thermal and low pressure and so forth, high pressure and all that. Now, the chemical vapor deposition process can be of various kinds, can have different kinds of reaction. Here is a decomposition of silane into silicon. Tungsten fluoride is reduced by hydrogen into tungsten, which is again an important part of the tungsten plug process in VLSI fabrication. Silane is oxidized into SiO2 and so forth. Now, all these are reactions that occur on hot substrates, and the temperatures required depend on the kind of reaction. So, it can vary from a couple of 100 degrees to several 100 degrees, and each of these is a case of heterogeneous nucleation. So, that reaction has to take place on the substrate surface, and then of course, as we discussed in the other day regarding the formation of regarding heterogeneous nucleation, much the same kind of a process is required. So, you have the diffusion of reactants and then the adsorption of reactants on the substrate surface, reaction taking place, and then the mobility of the growth species on the substrate to form this film through nucleation and growth, and then the ejection of reaction byproducts into the chamber, so that they are pumped out and so on. Therefore, just as in the case of a physical heterogeneous nucleation process, which we discussed a couple of days ago, this one also is a complex process that involves multiple steps. One thing to remember in the context of nanomaterials is that this process can be slowed down by controlling the substrate temperature, as long as the substrate temperature is high enough for the reaction to take place. If the substrate temperature is not high enough to allow the reaction to take place, of course, then there is no nucleation. But usually these reactions take place over a range of temperatures, and therefore, it would be possible to lower the temperature in order to get smaller crystals that are generated out of this heterogeneous nucleation process. So, one way to obtain nanostructured thin films is to lower the temperature of growth in a CVD process, as long as I said, as long as the reaction takes place at that temperature. Another way is to choose the reactants appropriately. What I have shown here is, there are numerous ways in which, for example, one can obtain silicon. This is trichlorosilane, you can have, as I showed in previous, you can have silane directly giving us silicon, you can have trichlorosilane giving us silicon. It is possible to alter these reactants so that it allows us to alter the range of temperatures or the conditions over which the reaction can take place, and that way to control the structure, the microstructure, the nanostructure of the resulting film. Now, epitaxial growth of gallium arsenide. Gallium arsenide is a direct band gap semiconductor, and we mentioned gallium arsenide and gallium aluminum arsenide in the context of formation of quantum wells for the formation of lasers, for example. Now, such an epitaxial layer is actually a single crystalline layer, but usually of a very small thickness. We mentioned thicknesses of the order of 1 or 2 nanometers. So, they are actually nanostructured in that sense. So, epitaxial growth of gallium arsenide is possible by the CVD process by using trimethyl gallium and arsine to obtain gallium arsenide typically at about 600 degrees Celsius. So, one gets high quality crystalline layers of a controlled small thickness through such a process. So, this epitaxial growth is actually an important part of nanostructured materials, because these processes can be controlled with great precision to obtain, let us say, precisely 10.4 nanometers of thickness of gallium arsenide, for example. CVD is versatile. A whole host of materials can be deposited by the chemical vapor deposition process, elemental semiconductors, compound semiconductors, oxides, nitrides and so forth. All of these can be, the microstructure of all of these things, or should I say the nanostructure of all these things, can be controlled by the choosing of the parameters of the CVD reaction. For example, microcrystalline silicon is an important part of technology under development. So, it is possible to obtain by the same CVD process not only single crystal silicon as shown here, but also microcrystalline silicon by choosing the appropriate conditions. Actually, microcrystalline is generally speaking of nanocrystalline dimension, nanometric dimension. So, nanostructures of a whole host of materials can be obtained in film form by the CVD process. The CVD process has various parameters which we control, as I was just saying, flow rates, deposition pressure, temperature, and the precursors themselves. As I said, there is usually a choice of these precursors. So, by choosing them, one can choose the conditions under which the reaction takes place, which influences the structure of these materials, the crystalline structure of these materials. Therefore, all these give handles on obtaining film material by the CVD process with a highly controlled set of structures possible. A whole host of precursors are there and so forth. So, this is a kind of a laundry list of different precursors, inorganic precursors. The point is that one should have volatile materials as precursors. That goes without saying, because this is a chemical vapor deposition process. So, silane is really gas at room temperature, tungsten hexafluoride is a gas at room temperature, titanium tetrachloride is a liquid at room temperature, but all of these have substantial vapor pressures which allow us to use them as precursor materials for CVD. So, these are all different precursors, and one of the things I mentioned is the formation of gallium aluminum arsenide, usually in epitaxial structures of nanometric dimensions, that is just obtained by having an appropriate proportion of the gallium precursor, which is trimethyl gallium, aluminum precursor, which is trimethyl aluminum, and then having the reaction with arsine at about 6 to 700 degrees to give us gallium aluminum arsenide of the chosen or desired composition. Similarly, nitrides, which are now of course of great technological importance in the context of blue and green sources of light. Ferrocene is another precursor that has been employed for the CVD of carbon nanotubes. This TEOS, tetraethoxy orthosilicate, is widely employed in semiconductor technology to produce SiO2. I mentioned metal organic CVD, which is again a particular process of CVD, particular version of CVD, where metal organic precursors are used, such as the acetyl acetonates and so forth, that would give films of metals and metal oxides, including complex metal oxides as listed here. It is a versatile process. CVD is a complex process because transport phenomena are involved, because gases are flowing, vapors are flowing. There is a whole variety of chemistry, and often reactions on the in the gas phase may occur. So, the design of reactors and the geometry of reactors and so on are quite important for the successful execution of chemical vapor deposition to obtain the kind of material that one wants. So, there are thermodynamic factors because there are chemical reactions involved, hydrodynamic factors because there is flow of gases and vapors involved, kinetics involved, both because of flow rates as well as because of temperature and the nature of precursors and so forth. CVD is a complex process, but fortunately it is possible to control it well, model it also to obtain materials of the sort that one wants, including very specifically nanostructured material. This describes the effect of temperature in an Arrhenius plot, how the deposition rate of films in a CVD process varies with temperature. Therefore, you have, because it is an Arrhenius plot, you have inverse temperature. So, we are talking about low temperature here and high temperature on the left over here. So, as the temperature is increased, the growth rate increases linearly in this region over here. So, this is the kinetic region. At a middle range of temperatures, the growth rate is essentially independent of temperature. So, this is the region where one would like to operate the CVD process, where the growth rate is relatively insensitive to temperature. This is how the concentration of the reactant, the vapor pressure of the reactant affects the CVD process. So, again over here where nucleation in the gas phase occurs, this is the region to avoid for the CVD process. One operates in this region where the deposition rate depends on the concentration of the reactant in a linear fashion. So, since the concentration of the reactant can be controlled quite well, one operates along this region to get the deposition rate one wants in a given process. Different types of reactors and the involvement of hydrodynamics and the analysis of the hydrodynamics of the reactors to obtain what one wants, and this all of this is very important for the semiconductor industry and done with a great deal of care. Again, flow patterns and the visualization of flow, so that one can design these things properly to obtain uniform films and so forth. Different kinds of configurations to obtain multi substrate reactor over here and so forth. So, these are all different versions of the reactor to obtain CVD films. This again a demonstration of the capability of CVD to provide us with conformal coverage. Now, so far we have dealt with CVD in the context of high technology applications, but CVD is also obtained or used to obtain cutting tool coatings for the machine shop actually. So, it turns out CVD is very effective in obtaining multi-layer coatings of aluminum oxide and carbide and nitride and so forth to enhance the tool life in cutting tool operations. So, CVD is used in such a much more mundane process as well. We will conclude there for today. So, what we have dealt with today is to review some general aspects of nanomaterials by the physical methods, and then we went on to discuss carbon nanostructures and how carbon nanostructure, in particular carbon nanotubes, and how carbon nanotube properties depend on the configuration of carbon nanotubes, and the production of carbon nanotubes by the chemical vapor deposition process. And then we went on to review the general aspects of chemical vapor deposition process and how it has advantages of the physical vapor deposition process and certain applications of the chemical vapor deposition process both in high technology and what we just mentioned at the end in mundane technology. We will continue with this discussion next time and then go on to discuss the analysis, the characterization of nanomaterials by different methods. Thank you.